SBQuantum is a startup, a spin-off based off of Institut Quantique in Sherbrooke, Quebec, so eastern part of Canada. And really our vision is to reap the full potential of magnetic sensing, and we're using quantum. So we're a 20 people business based, most of the staff in Sherbrooke. We have a few people in Montreal and also one person in Boston. And we're building the full stack of magnetic sensing, which not only limits to the hardware, but also the interpretation algorithms so that we can interpret the magnetic field signals in a way that's not being done before.
I read the news release about the launch of your quantum diamond magnetometer. Was that with SpaceX in March?
Yeah, so we launched just last Monday on a SpaceX rocket along with 110 satellites or something like that. So we've been working for the last few years with Aspire Global, and they actually launched 9 satellites on the same day. And we're one of the missions. Yes, we're at the last phase of this MagQuest program to build and maintain the world magnetic model. So we also launched alongside IOTA Technology and the University of Boulder with the Cosmo mission. And really the concept of the mission is taking our diamond-based magnetometer technology and using the high fidelity, high precision of diamond vectorial readings to build this essential asset that is the world magnetic model.
And are you getting any feedback from that launch yet? Are you able to get results so far?
Yeah, so we got the initial ping back from the satellite. So we're very happy that the launch was successful, that we can communicate with it. And now we're going, actually Spire is the one doing the commissioning, and they're going through a list of 30 different steps, and like booting the GPS systems, deploying the solar panels, and we're at the bottom of the list, interestingly. So we're still waiting eagerly to see the magnetic field data being outputted by our technology, because this is the first time a diamond magnetometer technology is going into the outer space. So we're very excited about that.
Oh, that's really cool. It would be great to hear when you start to get results back that are tangible.
Absolutely. We'll keep everyone posted on the social networks, that's for sure, and eventually release some kind of a white paper with the feedback we'll have from NGA and the NOAA, that we can benchmark our data with previous missions. And hopefully this is only the beginning. We'll send additional satellites in the future to produce even more accurate magnetic field maps.
Tell us why diamond, particularly technology-grade grown diamond, is so important to this work.
One of the challenges for the MagQuest program was measuring the magnetic field vector, so the way Earth's magnetic field is pointing, with a high level of accuracy. So currently, there's classical technologies like the flux gate magnetometers, and these will tend to drift with temperature. So that's an issue if you're thinking about building this global world magnetic map. So another way to do it is to use quantum-based magnetometers, such as atomic vapor magnetometers. However, these typically only measure the amplitude of Earth's magnetic field. So you have to apply some scheme with coils to vectorize, so to get the orientation of the magnetic field back. And that adds potential issues with the refresh rate and the fidelity of the measurements. So what's really wonderful about the diamond magnetometer technology is that within a small slab of diamond that I'm holding here, so the kind of a purple chunk of diamond here that's synthetically grown, contains 4 different sensing axes at the atomic level. So the nitrogen impurity from the NV center defect that we're using can be on 4 different lattice sites. So in effect, it creates a 4 sensing axis magnetometer. And we can combine that to infer in real time the temperature of the diamond and the vector magnetic field in a very small volume. So that's one important factor. And since everything is solid state, it's very rugged. So all the ancillary systems to control and read out the system is all optics based and based on non-resonant excitation and a collection of the light re-emitted by these defects. So all of that captured together allows for very accurate vector magnetic field readings because everything is based fundamentally on the laws of quantum physics. So we can always recalibrate, come back to the intrinsic calibration of the system. So the fact that it's vectorial, it's rugged, are key components which allowed us to progress into the MagQuest program.
What are the key performance indicators from this space mission that you are hoping to achieve? And if you achieve them, where does that take you next?
Great question. So actually setting the right metrics for the MagQuest program has been very helpful for SBQuantum because coming from a scientific background, so from a physics background, the typical way to develop technologies is to chase perfection, to chase the ultimate boundaries of what the technology can offer. However, for the MagQuest challenge, they were very pragmatic. So the objective was to measure Earth's magnetic field with the precision of 1 nanotesla over 50,000 nanotesla, which is the typical value for Earth's magnetic field. So that's roughly 20 ppm precision. So it's a good degree of precision over extended mission lifetime. And the second metric was the sensitivity. So the smallest magnetic field changes we could measure. And there, the metric is 1 nanotesla per square root of Earth. So meaning if you average the signal for a second, you will measure with the sensitivity of 1 nanotesla. So these are not like very stringent requirements. So some magnetometers, the best, like in very specific environments, will perform to femtotesla sensitivity, which is orders of magnitude better. However, to build a world magnetic map, the requirement is just 1 nanotesla. So that was very realistic, but at the same time ambitious for the diamond technology. So it really allowed us to focus our efforts onto maturing the technology and not chasing perfection. So speeding up the development so that like it's in a portable format, like I'm holding one here. So it went on drones, weather balloons, and airplanes. So it's very rugged and ready for field deployment. So maybe in terms of the second part of your question, what's next for us, especially for the space program, is that like this is a pilot mission. So we just launched in space. We're going to check the quality of the data produced by the CubeSat. And if we get the approval from NGA, we'll proceed to 20 years of procurement and sending a new satellite every 2 to 3 years, integrating our magnetometer technology and all the processing that's involved in producing the world magnetic map.
So you mentioned pre-testing it in somewhat harsh environments, but now it's in probably the harshest environment possible. I'm just wondering, what is the life expectancy of it in space?
So we're very hopeful that the limiting factor will not be the diamond technology itself, but actually the lifespan of the CubeSat, because it's placed in low Earth orbit, so at 600 kilometers altitude, and there will be some drag. So depending on the solar events, it might last 2 to 3 years in orbit. So that's the timescale we're looking at, and probably before it starts falling down too much, we'll send a new satellite as a replacement.